Oh, it is. So stop. Okay, great. Okay, so Riku will be looking at, passive sensing for detecting whether a children is hyperactive. So Riku's working with Maya.
Hello, my name is Riku. Thank you for introduction. I'm a PhD student at Carnegie Mellon University. Today, I'm very excited to present our work, LemurDx. This work was done in collaboration with New Realm and University of Pittsburgh. Globally, attention deficit hyperactivity disorder, ADHD, affects approximately 5% children. There are subtypes of ADHD, such as inattentiveness and hyperactivity. In school-age children, 55% of all ADHD cases show hyperactivity symptoms. Currently, measuring hyperactivity involves physicians' in-person observation or reports by parents or teachers, which prevent accessible measurement that is robust against subjectivity, potentially leading to delayed diagnosis or misdiagnosis. In this paper, we want to achieve objective measurement for hyperactivity by leveraging mobile sensing and eventually help doctors make decisions on children's hyperactivity. Researchers have used wearable sensors to measure the amount of body motion and correlated it with hyperactivity. For example, prior work suggested that there is a significant difference between the motion data of children with and without hyperactivity, measured at a wrist-worn device in doing specific tasks. While showing promise, these works assume the measurement of children's motion data via IMU sensors happen during specific activities in controlled settings. In other words, these experiments do not involve hyperactivity measurement during a child's typical day, which is critical since conducting multiple inspections is recommended in clinical practice. Here's a sample plot of data randomly extracted from acceleration data collected in different activities. The first row is a child without hyperactivity, and the second row is a hyperactive child. In fact, there is not much difference between the hyperactive and the control kids during, for example, sleeping, or exercise, or at school. However, the child with hyperactivity shows larger movement than the child from the control group during sitting quiet moments. This observation highlights the importance of making machine learning models aware of context that child is in. In sum, to achieve hyperactivity detection from smartwatches data worn by children freely in their daily lives, lack of context in the motion data is a challenge. In this paper, we propose an approach to contextualize those motion data and show a direction to leverage that model for supporting clinicians' decision-making. For the data collection, we built a custom application that recorded accelerometer data at 50 Hz that runs on Apple Watch, and heart rate, GPS-based location, and nearby Bluetooth devices are also collected. We mainly use motion data to build machine learning models to detect hyperactivity. We have yet to utilize other sensor data like GPS, heart rate, and Bluetooth data in a machine learning model, but the collected data can still be shown to clinicians and practitioners to contextualize the motion and child's behavior. At the end of each day of the data collection period, we asked a member of the family to log the child's activity at half-an-hour intervals. The activity labels consist of very rough 7 activities, such as sitting, quiet, sleeping, everyday household, exercise, at school, not wearing, and other. We gave the family members the option to reduce the annotation burden and provide the activity labels at the end of the day. This approach, no doubt, increases label noise because they have to recall what their child was doing throughout the day, but we optimize for user burden and compliance. We targeted children between the ages of 5 to 12 years. 68 participants completed the data collection. Out of this, 32 children had ADHD, and 36 were in the control group. The inclusion criteria for ADHD group included a diagnostic interview by a trained clinician. Out of the 68 participants, by filtering out error data, such as the case Apple Watch did not collect the data properly throughout the period. We had usable data from 61 total participants, and 25 had ADHD. Now I'll talk about the machine learning pipeline. This is the baseline model. We first apply featureization to the raw acceleration data, which generates useful features to characterize time series data, such as max, mean, or standard deviation. Then, we train machine learning models and compute the final prediction regarding whether the child has hyperactivity or not. The best result of the hyperactivity detection was 63% F1 score when we used random forest classifier. This relatively not high accuracy shows the challenge or difficulty of using the motion data collected in an unconstrained manner. So, here we utilize the activity labels provided by the parents. We introduce a way to leverage the contextual data, which is provided by children's parents. Here, we apply context filtering by focusing on data corresponding to sitting quiet moments based on our initial data observation. The result of the hyperactivity detection with this context filtering using parent annotated labels was 81.6 F1 score. But there is a significant improvement in estimating hyperactivity when using contextual information. Finally, we also try to estimate such contextual data to make a fully automated system without relying on parents' efforts. Here, we aim to develop a filter that finds moments corresponding to sitting quiet by using machine learning from the sensor data. As a result, our end-to-end pipeline achieved 78% F1 score in hyperactivity detection, which is comparable to the result when we use the parent annotated labels. This result suggests, though noisy and coarse, parent annotated labels are still reliable, and machine learning model that predicts them from sensor data is reasonably effective. Additionally, we made the machine learning pipeline more interpretable, which is critical to aid for the deployment of the system to support clinicians. In addition to the predicted label of children having hyperactivity or not, we also made the machine learning model output a risk score, which is a continuous value from 0 to 1 that corresponding to the likelihood that half an hourly data belongs to the hyperactive children. This value can be used for analyzing the machine learning model and also for developing a clinical interface. This visualization mockup shows an initial prototype informed by need-finding interviews with clinicians and enabled by this risk score. The physicians can use such an interface to assess a child's behavior by evaluating changes and trends of this risk score across different contexts, such as time, activity, and location. Currently, we investigate how such a tool actually helps clinician decision-making. We have more analysis regarding this hyperactivity risk score, and I'm happy to discuss them during the poster session. Thank you.
Okay, I'll move to that one.
Thank you, very interesting work. I wanted to make a question regarding the demographic differences. So research shows that the ADHD symptoms in males are different than the ones in females. Like boys tend to be more hyperactive and have more prominent symptoms compared to females who are have more internalized symptoms. Have you performed any assessments on how your model performs for boys versus girls? And have you thought of incorporating this information to prevent misdiagnosing?
Thank you. That's a very good point. So in our data set currently, the balance of the that is kind of balanced, the ratio of the gender, but we haven't actually looked at the difference between the results of the model. I think our risk score that I showed in the last of the slide might help us to understand the difference between the distribution of those risk scores between those different groups, demographic groups. So that's definitely, that we want to explore in the future. Thank you.
Thank you. So yeah, let's give a clap to Riku. Thank you.